Okay, so this lecture will continue from where we left off in class, and we'll be looking at several things today, one of which will be the types of organic reactions. So we had gotten as far as saying that organic chemists recognize four classes of organic reactions. The first of it was substitution, and we saw that substitution reactions essentially were of the type A plus BC give rise to AC plus B. In other words, one species A would substitute or replace another species B. There were several examples of those reactions. We could look, I think I gave you an example of monochloromethane plus cyanide, for example, would give rise to acetonitrile and chloride. And this reaction was called an SN reaction, which meant that it was substitutive. Right? This is a substitution reaction. And the subscript uppercase N meant that the initiating species was a nucleophile. And as a reminder, nucleophiles are electron-rich species or electron pair donors, and functionally that's what happened, right? So I could write this reaction in a sense as if the cyanide reacts with the methyl chloride, and the two electrons from the carbon, the lone pair of electrons in the carbon, are being used to form a new carbon-carbon bond, and as a result of the incoming electron pressure, the two electrons in the carbon-chlorine bond both go onto the chlorine, and what you end up with are your products, which I could sort of redraw as MECN, right, the same species, and chloride. And so the character of the incoming group here is a nucleophile. It's an electron pair donor, and so this is a nucleophilic substitution reaction, or SN. And I did point out that organic chemists would further categorize substitution in terms of the nature of the incoming species. We also saw that, for example, giving you the case of an aromatic compound, where I could treat the benzene, well, you don't know the circles yet, hold on. I can treat benzene, crikey, I can treat benzene with D plus, for example, and what I would get would be a substitution reaction, and that would give rise to the monodeuterio benzene. Okay, this reaction was also a substitution reaction, but this time the character of the incoming species is electrophilic, so I would call this an SE reaction, which means it's electrophilic substitution. So again, the way we name these is that you write the uppercase letter for the type of reaction, in this case substitution, and then a lowercase letter indicating the character of the incoming group. We can also have reactions of the type, if I take, for example, butane, and I treat butane with, say, bromine in the presence of light, or heat would work as well. We end up with, among the products, this compound, which is 2-bromobutane, and we get HBr. And essentially what happens is there are two H's here. One of them is replaced by a bromine, and the H that comes off assembles with the other Br atom, and you get this product. So you get 2-bromobutane and HBr. So this is called an SR reaction, where the R here refers to radical. Okay, so we can have different types of substitution reactions depending upon the character of the incoming group. Well, the other class of organic reaction is addition. And an addition reaction is one in which there is incorporation of the elements of a simple molecule, incorporation of the elements of a simple molecule, simple And by simple molecule, we mean things like HCl or H2O or Br2 or Cl2 or something of that type, etc., with simultaneous loss of a pi bond. With simultaneous loss of a pi bond. Right? That's an addition reaction. So, for example, if I take propene and I treat propene with hydrogen gas in the presence of platinum, I'll end up with propane. And you know, it's tricky to see H loss and gain when we write molecules in the bond line form, but you have to be careful about that because I've got 3 H's here, so nothing happened to that carbon. But this carbon only has 1 H, now it has 2 H's, so this carbon has gained an H. This carbon has 2 H's, now it's got 3. So literally what I did is I added an H to this carbon and an H to that carbon. So I've added or incorporated the elements of a simple molecule, HH, and I've simultaneously destroyed a pi bond. So this is called an addition reaction. I can actually call this one a hydrogenation reaction. Typically in organic chemistry, the suffix ation means addition of, and the prefix indicates what you've added. Okay. Now, as it turns out, I can do the same thing I did for substitution reactions and write these as A for addition and then indicate the character of the incoming species. Although we're not going to go into that much detail for the addition reactions. So this is a hydrogenation reaction. If I take the same compound and I treat it with chlorine, right, what I'll make is this compound. Right, I'll make the 1,2 dichloro product, and this would be a chlorination. Right, in other words, addition of chlorine. If I took this compound, this is cyclohexene, and I treat it with HCl, I'll end up with this compound. Okay. And that is a hydrochlorination, meaning that I added a hydrogen and a chlorine. And again, you want to be careful, right? Because what I did is I added the Cl to this carbon, and I actually added the H to this carbon. Because this carbon has 1 H, now it has 2. And you want to be very careful in bond line formulas to make sure you interpret the addition or the loss of a hydrogen atom. The additions are not limited to carbon-carbon single bonds, carbon-carbon double bonds, but they could occur, for example, with other types of double bonds. So I can take this compound and I can add HCN to it. That's a hydrocyanation. And what I'll get is a product that looks like this. I'll end up with something called a cyanohydrin as my product, which is not that relevant, but the point is I added an H to this O and a CN to this carbon, right? So I literally added HCN across the pi bond. Okay, CN goes here and the H goes here. It's not limited only to carbon-oxygen double bonds. I said also double bonds in general. It could happen with compounds that are alkynes. So if I treat an alkyne, for example, HCl, I'll end up with this compound. Right? I'll end up with the 2,2-dichlorobutane. That's also a hydrochlorination. And I can, for example, take this compound, which is a nitrile, and I can treat this with H2O in the presence of H plus as a catalyst, and what I'll end up with is this compound. Okay, and this really overall is a hydration reaction. So this is a hydration. This one is a hydrochlorination. Again, although this time I added 2 HCl's, and this one would be a hydrocyanation. Okay, and you can see the recurring theme of ation, meaning addition of, and the prefix indicating what you've added. Just again to be aware that what I did in this case is I added the CLs repeatedly as I've drawn it to this carbon and the H's to the other carbon. Okay, so I added Cl here and H here, then Cl here again, and an H here to break the second pi bond. So in addition reactions, I can break either one pi bond or sometimes two pi bonds. Now this last case is kind of interesting because I start off with a molecule having two pi bonds. The product only has one pi bond. What I've literally done is I've added H2O to the molecule, so that is incorporation of the elements of a simple molecule, water, with a simultaneous destruction or loss of a pi bond. And I did. I have two at the beginning, I have one at the end. What you notice that the pi bond at the end is not between the same pair of atoms. Here it's between C and O. At the beginning it was between C and N. Nonetheless, this is still an addition reaction because it has followed our rules, which are incorporation of the elements of a simple molecule with simultaneous loss of a pi bond. Okay? So those are addition reactions. As we'll see, additions can actually be categorized also as electrophilic addition. There is nucleophilic addition, and then there's also radical addition. There are actually a couple other types, but those are a little more difficult to see in this particular context because we haven't yet done mechanisms formally. So our first two classes of reactions are substitution and addition reactions. The third class is elimination. And elimination reactions really are the reverse of addition reactions. These are reactions in which there is loss of the elements of a simple molecule with simultaneous formation of a pi bond. So this is really the reverse of our definition for addition. In addition reactions, there's incorporation rather than loss of the elements of a simple molecule with simultaneous loss of a pi bond, whereas here in the case of elimination, we are losing the elements of a simple molecule and we're forming a pi bond. For example, many of the reactions that we saw earlier as addition reactions, the reverse literally would be eliminations. So, for example, I could take this chlorocyclohexane, which I made by addition of HCl to the alkene. If I treat this with hydroxide, aqueous, and heat, it would make the alkene. And that reaction is an elimination reaction because we've lost the elements of a simple molecule, HCl, and we have simultaneously formed a pi bond. What is interesting to note here is that the inorganic products of this reaction, in fact, are water and chloride. So that nowhere in this reaction do I actually make HCl. In fact, I actually couldn't, because if, for example, HCl could not persist under conditions that are basic. What I actually make are water and chloride. But my definition for elimination is not that we generate HCl, but that we lose the elements of a simple molecule. So from the organic molecule's perspective, it has lost an H from this carbon and a Cl from that carbon. That HCl is not a product of the reaction is irrelevant. Okay, so I don't have to lose HCl, I don't have to form HCl for the reaction to be an elimination reaction. All that has to happen is that HCl must be lost from the organic compound. And by the way, I'd call this reaction a dehydro, in this case chlorination, dehydrochlorination. I was going to say halogenation, but I can be more specific. dehydrochlorination, because I know that the species being lost is HCl. So the logic here is that ation means addition of, but D is the opposite, right? So a D something ation is the loss of something, and the term in the middle tells you what you're losing. So dehydrochlorination is a loss of a hydrogen chloride. Similarly, I could take this molecule and I can heat it with concentrated sulfuric acid, and what I'll end up with is the alkene, and I would call this a dehydration reaction. Right? This will be called a dehydration reaction because it is the loss of water. Okay? Another dehydration reaction would be one in which we took the amide and treated it with P2O5. And for now, the reagents do not make a big deal, right? You're not responsible yet for the reagents. You pick this up as we go along. This is also a dehydration reaction. So it turns out that in neither one of these cases, the first and the third in particular, do we actually make, in this case, we don't make water as a product. In the top case, we don't make HCl as a product. But from the organic molecule's perspective, what it has lost here is H2O, so that's a dehydration. Certainly H2O here again, and this time HCl. And another good example of that is if I take this compound and I treat it with, say, sodium iodide in acetone. The product of the reaction is an alkene, and I actually make I2 and 2Br minus. Okay, so the product of the reaction is the alkene. The organic molecule has lost the elements of Br2, even though Br2 is not a product of the reaction. I make iodine rather than bromine. The bromines come off as Br minus. The fact that I don't make bromine as a product is irrelevant, right? As far as the organic molecule is concerned, it has lost the elements of bromine, even though it did not make bromine as a product per se. So those are elimination reactions. Again, you can subclassify elimination reactions in several different ways, but we're not going to get into those in as much detail. The last class of reaction that is recognized by organic chemists is a rearrangement. And rearrangement reactions can either involve rearrangements of hydrogens, rearrangements of hydrogens in a molecule, or carbons, in which case this one is called a skeletal rearrangement. So for example, I could have a reaction in which if I take this compound, let's see, if I take this compound and I simply dissolve it in DMSO, and DMSO is an acronym for dimethyl sulfoxide. Right, this is dimethyl sulfoxide, which has the structure S double bond O and two metals on it. This is an extremely polar organic solvent. If I dissolve this compound in DMSO, the product of the reaction is going to be this. Okay? And this is kind of interesting because if you look, I've got 1, 2, 3, 4, 5, 6 carbons in the starting material. I have 1, 2, 3, 4, 5, 6 carbons in the product. But whereas one of the carbons at the beginning was a quaternary carbon, this was secondary and that was primary. So I had a quaternary, a secondary, and a primary carbon. In my product, I have a well, of course, plus I have these were also primaries. Here I have a tertiary carbon, and of course a bunch of primaries. In other words, my quaternary and my secondary carbons my designation no longer exists. So what has clearly happened is one of these methyl groups moved across the molecule from this position to that position. Right? So in a sense, there was a migration of this methyl from that position to that position. That's called a skeletal rearrangement. Rearrangement reactions, or rearrangements in general, can either occur on their own, as in this particular case, where all I did is I simply dissolved one compound in the MSO, and it's the compound rearranged to an isomer. But rearrangements can often accompany other reactions. And so a good example of that is, I'll give you an analogous illustration. If I take this alkene and I add HBr to it, then the product of the reaction turns out to be this compound. Right? And that should look familiar. The product of the reaction turns out to be this one. Okay? And this reaction then really fulfills two criteria. It involves a rearrangement, right? Certainly, this methyl has moved over to that position. Wait a minute, no, I think I added one carbon too many. 1, 2, 3, 4, 5, 6, yeah, this compound. So if I add HBr to this compound, I'll make this one as a product. So there's clearly a rearrangement where this methyl has walked over, right, that's skeletal. But it's also by definition an addition reaction, because I have added the elements of HBr, the elements of a simple molecule, and there has been simultaneous loss of a pi bond. Now, it's a little bit more difficult to see the HBr being added. It's easy to see the Br coming on, that's really obvious. But clearly we must have done an addition because the pi bond is gone. So that even if we can't tell immediately that there's been incorporation of H, we must realize that in addition reactions and in elimination reactions, reactions that involve a pi bond, I must perturb two carbons, and the carbons will be adjacent. So either I take off groups from adjacent carbons, right? For example, in our elimination reactions, right? I'm taking off an H and a Cl from adjacent carbons, an H and an OH from adjacent carbons, an H2 and an O from adjacent atoms, a Br and a Br from adjacent atoms. So in elimination reactions, I must lose something, one group from each of two adjacent atoms, typically carbon, but it doesn't have to be carbon. In addition reactions, I'm going to do something to two adjacent atoms, right? In the case of the hydrocyanation, I added Cn and H to the C and the O. I added Cl and H to the C and the C, right? I added O and two H's to these nitrogens, to the nitrogen and the carbon. I added H and H and Cl and Cl. So in addition reactions and in elimination reactions, I must perturb two adjacent atoms. So I would call this reaction then, I would say this is an addition with rearrangement. Right? And take one more example. If I took this compound, and I'll just keep with the same set, if I had this compound and I treat this compound with let's say HBr, okay, I'll end up with this species. This would be a substitution with rearrangement. Okay, I can also have elimination reactions that accompany rearrangement. So, for example, if I had this compound and I treated that with conc sulfuric acid and heat, the product of the reaction would be this one. Right? And clearly this is a rearrangement because I've gone from a 5-membered ring with a 1-carbon appendage to a 6-membered ring. And the compound is an alkene. I had no double bonds at the beginning. I've got a double bond at the end, which means I must have lost something. What would I have lost? Well, clearly the OH, and we therefore must conclude we've also lost an H, because I can't just lose an OH from the molecule. And if ever you're concerned, work out the formulas. So the formula of this compound is C6, right? So it's 5 carbons in the ring and 1 here, that's 6. H2, 4, 6, 8, 9, 10, 12, O. And my product is C6H, 2, 4, 6, 8, 9, 10. So literally the difference between the two, C6H10, is literally H2O. Right? So clearly what has happened is the system has lost a water molecule. So this is a D, well technically it's an elimination with rearrangement, but I can be more specific and call it a dehydration. Right? Dehydration with rearrangement. And let me just check what I call these. Yes, I couldn't say much more. Yeah, so with this one, right, the top one, I could be more specific. Instead of saying addition, I could have called this, be more specific, a hydrobromination with rearrangement. Okay? So if I want to be more specific, I could call it a hydro. In other words, I could say what I've added. The same way here in the dehydration, I said which group was eliminated. Okay? Right, so there are 4 classes of reactions then, which are again substitution, several different categories, addition, elimination, and rearrangements. Well, we mentioned before that bond formation in organic chemistry typically involves some sort of a nucleophile attacking an electrophile. So, typically bond formation, right, so bond formation is typically typically involves a nucleophile plus an electrophile. And we gave an example earlier where, for example, cyanide acts as a nucleophile and attacks methyl chloride. So I'm going to form a bond using the 2 electrons from the carbon as the electron source. This is a nucleophile, this is an electrophile because the carbon is attached to a more electronegative element. So there's a delta plus on this carbon, a delta minus on the Cl. As this electron pair comes in, this carbon can't hold on to more than 8 electrons, and so it lets go of these 2. We'll see this in some more detail later on. And I end up with my product. Right? I end up with CH3, Cn, and bichloride. We call this an SN reaction. So bond formation typically involves then some nucleophile attacking some electrophile, or an electrophile attacking a nucleophile. Nobody really cares about the semantics. Well, bond breakage, right? Bond breakage, or bond lysis, right? When you lyse something, it means you break it. Really can occur in one of 2 ways. Either the 2 atoms in the bond are homonuclear, in other words, the 2 atoms are the same, and when the bond breaks, it breaks in such a fashion that each atom gets 1 electron. Now, it's perfectly fine to draw it this way. Now, there are 2 electrons in this bond. What this arrow means that 1 electron goes to the atom on the right. It's understood then that the other electron goes to the atom on the left. And so what you end up with will be an X dot and an X dot. Now, I could have just as easily and just as completely written it as X, X, and just shown 1 arrow. The 1 arrow means an electron from the bond, the 2 electrons, 1 goes onto this carbon. That means it's understood the other carbon gets the other electron. So however I want to write it, this is perfectly fine. Now these 2 species are free radicals. They're both free radicals. And therefore this kind of bond cleavage, where I generate 2 particles that are alike, is referred to as homolysis or homolysis. So homolysis is bond cleavage that generates a pair of free radicals. Okay? Homolysis actually happens to be encouraged by having bonds that are non-polar, or weakly polar bonds. It's encouraged in non-polar solvents or in the gas phase, and it's encouraged by heat and by light. So a good example is if I take Cl2 and either I heat it to 250 degrees Celsius or I expose it to light in the gas phase, and I end up with 2 chlorine radicals. And that simply occurs this way. And this is a classic example of a homolysis. So the bond is non-polar, okay? It's encouraged in the gas phase, and it's done in the presence of either high temperature or light. And I'm going to go through these features in a little while when we consider the other type, which is heterolysis. So in addition to bond breakage, which can occur in a homolytic fashion, there's also heterolytic bond cleavage or heterolysis. So this would be a case where I have an XY bond, preferably a polar one, in which one atom, the more electronegative of the two, absconds with both electrons in the bond. That would generate X plus and Y minus. Now this should be fairly obvious. Here, X and Y are both neutral. So when X has a share in the one electron, has one electron in this bond, and Y has one electron in this bond, they are neutral. So if X gives up the electron it was sharing to Y, so Y gets its electron and X's, then Y will be negative. If X then has lost the electron it put into the bond, then X is going to be positively charged. So I don't need to know the details of the Lewis structure of X, nor do I need to know the identity of X and Y. Right? I should be able to recognize that if I have these two neutral species and both electrons go into the atom on the right, then I'm going to get bond heterolysis, and I'm going to get a pair of ions. So these two species together are referred to as an ion pair. Right? This, of course, is a cation. This, of course, is an anion, and they are very separate type of species. And because their characters are so different, I'm going to call this lysis of the bond heterolysis, meaning that I've created two different kinds of species. Well, obviously, heterolysis then will be encouraged by polar bonds, right? And the more polar, the better. It would occur in polar solvents, and it would occur under ambient conditions. In other words, no excessive heat and certainly no light, right? Well, let's talk about then the contrast in the conditions required for heterolysis and homolysis. And let's start with heterolysis. So if I want to cleave a bond in a heterolytic fashion, obviously the bond should be polar, because what I want to do is essentially to take both electrons in the bond and dump them into one atom. That will only be allowed, or certainly be encouraged, if one of the atoms had a far better pull on the electron pair than the other. So if I were to have a bond that were polar, where one atom is already sucking electrons towards itself, then that would encourage heterolysis. I could look at it another way. I can say if the bond has two different atoms in it, the Cl in this case is much more electronegative than the H, which means the electrons, which by right should have been bang smack in the middle, are not going to be. They're going to be somewhere. They're going to be somewhere here, because the chlorine pulls it better. So therefore, I just need a little bit more help, a little oomph again, for those electrons to be dumped entirely on the chlorine. So the more polar the bond is, right, the less work I have to do in essence to just sort of have these two electrons locked off completely onto the Cl. So it still is encouraged by polar bonds. If the bond was non-polar and I wanted to get both of these electrons now, which are equally shared, onto one atom, that's going to be hard, because I've got to push these electrons now all the way across here, and one of these atoms has a pretty good pull on the electrons, so it would be hard to move the electrons away from one atom who has an equally good pull on those two electrons. So heterolysis then is encouraged by polar bonds. Well, of course it's going to also be encouraged by polar solvents, because the breakage of this bond does not happen on its own. What will happen is, let's say I have this in a polar solvent like water. I'm going to draw a single water molecule. The water molecules are going to orient themselves so that the delta plus of a water molecule is going to point towards the delta minus of the bond. So the delta plus end of the water points towards the delta plus end of the bond. The delta minus end of the water points towards the delta plus end of the bond. Bonds are forces of attraction. So literally what's happened is that the Cl is being pulled from the right, the H is being pulled from the left. And I've only drawn one water molecule here and one water molecule here. In reality, there'll be dozens of water molecules, there'll be hundreds of them, sort of jostling for position around the H, and another 100 or so jostling for position around the Cl. So the combined pull of those several water molecules on the right and on the left will assist in the cleavage of the HCl bond. I mean, they literally rip the bond apart. If the molecule is non-polar, then the best I can do is form van der Waals bonds. Right? Van der Waals bonds are not particularly strong, they will not help in the scission of the bond. Therefore, heterolysis would be encouraged not just by polar bonds, but by polar solvents. The other point is, not only do solvents play an important role in the separation of the two atoms, in other words, in the breakage of the bond, but also in the stabilization of the ions that are generated. So if I were to break this up and made Cl minus and H2O and H plus, you have to recognize that now hundreds of water molecules will assemble around the H plus and around the chloride in what are called solvation shells. And those solvation shells will have water molecules with the H's pointed on the inside, right, with delta pluses to stabilize the chloride, and with the O's on the water molecules pointed towards the inside to stabilize the H. Hundreds of them will solvate, this is called solvation. Hundreds of them will solvate the ions and therefore stabilize them. So the solvent plays a role both in the breakage of the bond and in the stabilization of the ion pair that is generated. A non-polar solvent would not be able to stabilize the ions because you generate only van der Waals bonds to stabilize the ions. And the ions would essentially therefore be relatively naked in that medium. They're very, very weak bonds, and it's not to the system's benefit to generate ions in a non-polar medium. So my conditions that favor heterolysis then are polar bonds, polar solvents. And of course, I don't need massively energetic conditions if I have these two, because the polar bond encourages the ionization as does the polar solvent. And so I don't need to be putting in large, massive amounts of energy. In contrast, if I want to get homolysis, then of course I want the bond to be non-polar, because I want the two atoms, I don't want either atom to have a much superior pull on the electron pair than another one, because that would tend to promote heterolysis. I also want the solvents to be non-polar, because if I put this molecule in a solvent which is polar, say delta minus, delta plus, then what will happen is the delta minus of this molecule would tend to repel the electrons in the bond away from here. And that will therefore create a dipole, a delta minus and a delta plus, in this molecule. What that will then do is take the molecule on this left will orient to get a delta plus and a delta minus, and so I'll now start to get bonds, and that will assist in the breakage of the bond. I don't want that to happen. So I don't want to put my non-polar molecule in a solvent that is polar, because polar molecules will tend to induce dipoles on the non-polar bond. And if I wanted the bond to break in a homolytic fashion, I do not want significant dipoles generated along the bond. So it's not to my advantage, if I want to promote homolysis, to put the molecule in a polar solvent. So I want the solvent to be non-polar, or in the gas phase where there's simply no interactions between the molecules. And because I'm not getting assistance from the solvents in terms of the kind of assistance I get in heterolysis, and I'm really not getting assistance from the bond either because the electron pair will be bang smack in the middle, I would have to compensate by putting in extra energy. And if I would need large amounts of heat or the presence of light, which packs quite an energy wallop, to cause the bonds to undergo fracture. So I would need heat and light to promote homolysis. So bonds then can break homolytically or they can break heterolytically. It turns out then, if you notice, we've generated 3 different kinds of species in this discussion. We generated species that were free radicals, we generated species that were cations, and species that were anions. Right? We have free radicals, we have cations, and we have anions. It turns out that carbon can actually form these 3 species, and those 3 species will form the basis of what we call carbon-based intermediates. So the carbon-based intermediates in other words, intermediates that carbon forms are free radicals. And free radicals essentially are carbon atoms that are neutral and have a free electron. So they're neutral, trivalent carbon atoms. With an unpaired electron. Those would be free radicals. The second class would be carbocations, which are cations. These are also trivalent, but now the carbon is positively charged. So these are positive trivalent carbon species, right? These only have a sextet of electrons. So this carbon has 2 electrons in this bond. There's 2 here, 4, 6. This is 2, 4, 6, and 1 is 7. And of course it's neutral because if I count the electrons that belong to carbon, it's 1, 2, 3, 4. If I count the electrons that belong to carbon here, it'll be 1 in this bond, 1 in that bond, 1 in that bond, that's 3, 1 less than the number, hence a positive charge. The third carbon-based intermediate that we talk about for now is the carbanion. And carbanions are also trivalent, but the carbon now has a lone pair of electrons and consequently a negative charge. Because if I count, it'll be 1, 2, 3, 4, 5, which is 1 more than the group number. But of course it has an octet, because if I count all the electrons on the carbon, it's 2, 4, 6, 8. So these are negative, trivalent carbons with an octet and a lone pair of electrons. Okay? So these are the 3 classes of carbon-based intermediates. These are free radicals, carbocations, and carbanions. Now, remember these are called intermediates, and so what that suggests is, if you guys remember, several weeks ago we were looking at reaction profile diagrams, enthalpy against reaction coordinate, and in those we would have reactions where we do things like this and whatever else and so on, right? And we say this would be an exothermic reaction, it would be a 3-step exotherm. Well, the things that live here, right, these intermediates, this might be our carbocation, or it might be a free radical, or it might be a carbanion. This is where these things reside, right? In these little wells, these energy hollows, or these energy minima. So the carbon-based intermediates can reside there. So for example, if I look at this reaction, and I take, say, this compound, and I treat it with water, what I end up with as my product, right, would be the alcohol, and I'll make HCl. So this is a substitution reaction. I can call it an SN reaction because the species, the character of the incoming species, the water, is a nucleophile. Well, if I draw the reaction profile diagram for that reaction, it turns out what I actually get is the following. I have this step, this step, this step. Let's see here. I'm not being silly. That's actually why I picked that one to begin with, because it's actually the same thing. So what I get is that reaction. What the heck is this? Why is that not coming out? Yeah. Right? So it turns out that the species that lives here, so if I start off, right, this is my reagents, which would be this compound and water. These are my reagents together. Right, this is my R. Here, the species that I actually make is a carbocation. Okay, that is what I make here. And the species that I have here turns out to be this compound, or this species. Right? So that's a species where the plus charge is on the oxygen. So this is called an oxonium ion. Right? It's not a carbocation, but it's an oxonium ion. But those are the intermediates that live in these hollows. Okay? And of course, my product of the reaction, as I said, is going to be the alcohol. Okay? The alcohol and HCl. And in fact, what we'll be doing in very short measure is looking at mechanisms of reactions, exactly how we transform the reagent into the product. Okay, so I'm going to stop. Well, this. All right, so let's start looking at mechanism and what we mean by mechanism. So the mechanism of a reaction, essentially, and this is a working definition, you'll never be asked to define mechanism, but a mechanism of reaction provides a moving picture that details how the reagents are transformed into product, right? So it provides a moving picture, detailing how reagents go into product. It has to must identify any and all intermediates along the reaction pathway, as well as their order of formation and decay, right, and their order or sequence of formation and decay. In other words, when are they formed, when do they die? It must account for the observed stoichiometry. In other words, if I tell you it's 1A plus 2B gives 3C, then when I write the mechanism and I add the steps together, this must be true. So the stoichiometry of the reaction is just a measure of the coefficients of the reagents, right? So if I say it's 2A plus B give 2C plus D, when I sum the steps of my mechanism, this must be what I get. It must also account for the observed, so account for the observed stoichiometry, kinetics, stereochemistry, etc. And 4, it must clearly identify rate determining step of the reaction. Rate determining step, right, or the RDS of the reaction. Some people call the rate determining step the rate limiting step of the reaction. So a mechanism then has essentially 4 burdens. It must tell you how the reagent forms a product, details of the steps. If the reaction does make any intermediates, not all reactions do. Some reactions, remember, can be synchronous, so they don't make intermediates, right? It must identify, if it does make intermediates, it must tell you when are the intermediates made, step 1, step 2, and whatever, and what those intermediates are. What do they decay into as the reaction progresses? It must account for the observed stoichiometry, the observed kinetics, the observed stereochemistry, and so on and so on and so on. It must also clearly identify the rate determining step of the reaction. So how do we proceed from here? Well, let's say I tell you that I have a reaction in which, say 2A, I'll do the one I had earlier, plus B gives rise to, let's say, C plus D. And I say this reaction is an endotherm, or is an exotherm. So let's say one lab somewhere in Germany says that the mechanism, let's call it mechanism 1, this person proposes a mechanism that says the way this reaction goes is that 2 A's come together. So I mix 2A and B in the pot, but 2 A's come together and they form M. Then M reacts with B, and that forms C plus D. Now, when I sum the steps together, the things that are present on the right and on the left I can cross out. So that overall, 2A plus B gives rise to C plus D. And let's say this lab suggests that step 1 is the RDS. Okay. Somebody in Australia says that's not right at all. Our studies indicate that it's a different mechanism. In our mechanism, A and B react to give rise to Q. Q then breaks down on its own to give R. R then reacts with A to give rise to C plus D. And according to their studies, they find that step 2 is the RDS. Now when I add the steps together, Q goes out, R goes out. And overall, 2A plus B gives rise to C plus D. Along comes a third lab somewhere in, let's say, California. They say, no, both of you are wrong. The correct mechanism is that B, first of all, gives rise to W, and then W reacts with an A to give C plus Y, and Y then reacts with A to give rise to D. And they say that step 1 is the RDS. When I add these steps together, the intermediates W go out, the intermediate Y goes out, and overall 2A plus B gives rise to C plus D. Now, this is the point I was making about the mechanisms providing a sort of a moving picture, right, of how the reagents are transformed in the product. It also tells us what intermediates are generated, right? I make M in this one, and then M is at the end of first step I make M, then M is destroyed in the second step. This says I make intermediate Q, which generates intermediate R, right? And this says I make W. W then decays to make Y, and then Y decays in the presence of A to make D. So it tells me, it clearly identifies any and all intermediates along the reaction pathway and their sequence of formation and decay. It tells me clearly which step is the RDS, and it accounts for the observed stoichiometry, right? When I add the steps together, I get 2A plus B gives C plus D. So the question is, how can I tell which one of these is correct? Now let me just sort of put in a point here very quickly. There is no such thing as a correct mechanism. The best I can say is that a mechanism is consistent with the observations. I can say the mechanism is wrong, meaning it's inconsistent with some of the data, but I can never say a mechanism is right. The best I can do is say that a mechanism is consistent with my observations. So then, how would I propose to distinguish between these three mechanisms? How would I propose to critique these mechanisms? And the answer is, I'm going to use kinetics, right? And you've actually seen this in your Gen Chem already. I'm going to use kinetics. And we're going to use a method called the method of initial rates. Method of initial rates. Well, in the method of initial rates, what I'm going to do is I'm going to generate stock solutions of A and B. Those are my reagents. And I'm going to measure some initial concentration of A, some initial concentration of B. I'm going to measure the rate of the reaction, and then I'm going to get the relative rate of the reaction. Okay, so I'm looking for four things. And I would say, for example, that let's say, for example, so let's say I have let's say I have 0.5 molar A, 1 molar B. I now have 1 molar A and 1 molar B. Then 1 molar A and 2 molar B. So I'm going to make up two stock solutions, 1.5 molar A and 1 molar A. 1 molar A, 1 2 molar A. And I'm going to measure the rates of the reaction. So let's say I find the rate to be, let's say 4 by 10 to the 2, whatever my units are. Then, let's say I double the concentration of A, and I find now that my rate of reaction is 1.6 by 10 to the 3. I keep this constant, I double that, and I find that my rate is now 3.1. Oops, that's exciting. I find my rate now is 3.1 by 10 to the 3 units. Well, I'm going to take my smallest rate and call that unit. So that's my relative rate is 1. So this number is clearly 4 times that number. So I'm going to call this number my relative rate 4. And this number is roughly 8 times this number. Right? It's an experimental error. So I'm going to call this number 8. So those are my relative rates. Now, if you notice then, I've done several things. I've only made up 2 stock solutions of each reagent. I am changing the concentration of one reagent at a time. So this is my reference line. I kept the conc of B constant, and I doubled the conc of A. Then I kept the conc of A constant, and I doubled the conc of B. And I measure the rate of the reaction. Now, 2 points. How do I measure the rate of the reaction? Well, I'm looking for some event. So it may well be that when A and B react, both A and B are colorless, but one of the products, or maybe both of them, are colored. And so as the reaction progresses, let's say that they're blue. As the reaction progresses, the mixture gets bluer and bluer and bluer. So for example, I can have a light meter, right? I have a light meter, calorimeter, that measures the light intensity. And I can tell the machine, look, when 20% of the light is blocked, beep. And I can just tell that it beeps after 20 seconds or after 2 minutes or whatever. So I have a sense of the time that involved, and I know that 20% is a certain measure of the concentration change. So I know a change in concentration, a change in time, I then get a rate. It could be that A and B are neutral, but one of these products is acidic. So I can add an indicator at the beginning, and when it changes color at a certain pH, then I can stop my stopwatch. Or it could be that A and B are in solution, but one of these compounds precipitates out. And as it precipitates out, again, it's going to sort of block the light, and it's going to get cloudier and cloudier and cloudier. And again, I can use a calorimeter to measure the light intensity. So whatever it is, I can find some event that I'm going to use to mark some point in my reaction. So that's how I measure the rate. You will notice for each of these reagents, at the very bottom, there's a subscript 0. And the subscript 0 means we're using a method of initial rates. And there's a reason we use the method of initial rates. Right? In other words, we are measuring the rate of the reaction. We're measuring the rate of the initial reaction. Right? Typically in the first 5 or 10% of the reaction. We never wait until the reaction is halfway done to measure the rate. We measure the rate in the first 5 to 10% of the reaction. And there's a reason for that. There are reasons for it. And the reason simply is we get better data when we measure the rate at the beginning. Why do we get better data? Well, we get better data for two reasons principally. One is because the rate of a reaction decreases as the concentration of the reagents decrease. Therefore, since the concentrations of my reagents are highest at the beginning, my rate is highest at the beginning. If my rate is highest, what it means is my number is big. And the bigger the number you're measuring, the less likely you are to find errors or to create errors. For example, if I ask you, if I have, there might be 20 of you guys in the class, right? There are 20 students in the class. And if I ask you to count the number of students in the class, and for some reason you count 18 rather than 20, well, that's a difference of 2, and that's a small number, but it's 2 out of 20. That is a 10% error that you've made. If I ask you to count the number of people in the McNeese campus, and there are 8,000 students, and you're off by 2, well, that is 2 out of 8,000. That is, I don't know what that is, that's 0.0025%. That's nothing, right? So if the number you're measuring is a big number, small errors become insignificant, right? Because of the sheer number of the sheer number that you're measuring. But if the number you're measuring is small, small errors get magnified. So I want to measure the rate when it is largest, and I can get that at the beginning of the reaction. That way I get very little error in my measurement. So I get more reliable data. The other reason that we use the method of initial rates is that sometimes the product of a reaction turns around and interferes with the reaction. And a good example of that is here. If you take an ester and you treat an ester with water, the ester will undergo a process called hydrolysis, and it will generate a carboxylic acid and an alcohol. The problem is the reaction gets faster and faster and faster because the carboxylic acid turns out to catalyze the hydrolysis. So normally a reaction should slow down as your concentration of reagents falls. But with hydrolysis of esters, what you get is autocatalysis. You get autocatalysis, right, where the reaction catalyzes itself because one of the products of the reaction interferes with the reaction rate. So I'm much better off measuring the reaction rate when there's very little product. Because if the product turns around and interferes with the reaction, I want to measure the reaction when there's not much product that can cause problems with the rate. So that would be at the early stage of the reaction, before much product is formed. So we measure the initial rate. So we measure the initial rate because we get better data, right? We get better kinetic data, better data on the rate. Better kinetic data at the beginning. we get better kinetic data at the beginning, right, at start, right, and this is typically 5 to 10% of reaction, and we get better data because of A, larger rates, and B, minimal product interference. Okay, so let's get back to that table we had, and I'm going to get a new page. Let's get back to that table we had. So we had conc of A, subscript 0, that means initial concentration. Conc of B, subscript 0. And then we had, what did we have? We had rate, and we had relative rate. And I'm going to go straight to relative rate, okay? Because we talked about how we get rates already. And I don't quite recall the number. Yeah, I did. It was 0.5 molar 1, 1.0, 1.0, 4, and then 1.0, 2.08. Okay. So why am I interested in the kinetics? Well, I'm interested in the kinetics in order to try to elucidate, to figure out the mechanism. And what is it that I want? And the answer is I want an equation that tells me the rate of the reaction is equal to some constant, the rate constant, times the concentration of A to some power A, times the concentration of B to some power B. This term, this equation, is called a rate equation. This is called a rate equation. K is called the rate constant, which, big surprise, is a constant that varies only with the temperature. So if I keep the temperature constant, it doesn't matter what these are, the rate constant is the same. The rate equation is important because the rate equation tells us which species, right, which reagent species, and how many of them are involved in the reaction up to and including the rate determining step. So the rate equation tells us which reagent species, A and B, and how many of them, 1A, 2A, whatever, are involved in the reaction up to and including the rate determining step. And that's important because if you look at the mechanisms that were proposed, it'll be able to tell me, well look, were there 2 A's that were involved up to and including the RDS, or maybe it was an A and a B that were involved up to and including the RDS, or maybe it's just a B alone. Okay? So I can immediately, and if I have that information, I can immediately say mechanism A, mechanism 1 is consistent, but mechanism 2 and 3 are not consistent. Okay? So the rate equation is very important, which is why it's critical that I get good kinetic data so we can get information in the rate equation. So how do we get the rate equation? Well, it's actually very simple. It turns out that, well, I'm sorry, one other thing. The term little a and little b are the orders of the reaction with respect to reagent A and reagent B. So little a is the order of the reaction with respect to reagent A. Little b is the order of the reaction with respect to reagent B. The overall order of the reaction is the sum of A plus B. So how do I get little a and little b? Here's what I do. It turns out whatever I do to the concentration of one reagent, I do to the rate raised to the power of the order of the reaction with respect to that reagent. I'm going to say it one more time and then I'm going to illustrate. Whatever I do to the concentration of a reagent, I do to the rate of the reaction raised to the power of the order of the reaction with respect to that reagent. For example, going from 0.5 to 1, what have I done? The answer is I multiplied by a factor of 2. I'm not worried about the conc of B because I kept that constant. Therefore, if I multiplied conc of A by 2, it means I would have multiplied the reaction rate by 2, raised to the power of little a. So I can now say then that 2 to the a is equal to 4, because when I multiply this rate by 2 to the a, I go from 1 to 4. Therefore, I multiplied it by 4. So 2 to the power of a is equal to 4. But 4 is 2 to the power of 2. Therefore, a is equal to 2, and the reaction is second order in A. What does that mean? It means then that A is involved in the reaction up to and including the RDS because it's in the rate equation. It also means that 2 A's are involved in that reaction. Okay, well, keeping conc of A constant, I doubled the conc of B. Well, if I double the conc of B, I would multiply the reaction rate by a factor of 2 to the power of B. Therefore, 2 to the power of B is equal to 2, because 4 to get 4 to 8, I multiply by a factor of 2, and that's 2 to the power of 1. Therefore, B is equal to 1. So my rate equation then becomes rate is equal to K times conc of A squared times conc of B to the power of 1. We're all adults, so we roll right to 1. So what does this tell me? It tells me that 2 A's, and 1 B are involved in the reaction up to and including the rate determining step. 2 A's and 1 B. So I'm going to go look at these mechanisms, the ones that propose in, I think, Germany and wherever else it is. Well, this isn't right, because this tells me that 2 A's and no B's are involved in the reaction up to and including the RDS. So this mechanism 1 is wrong, because according to kinetic data, 2 A's and 1 B are involved in the reaction up to and including the RDS. If this mechanism were correct, the rate equation would have been rate is equal to K times conc of A squared, because it means 2 A's and no B's were involved in the reaction up to, and there's no up to here, and including the RDS. What about mechanism 2? Well, this is also wrong, because according to my kinetics, 2 A's and 1 B should be involved up to and including the RDS. Well, this tells me 1 A and 1 B are involved in the reaction up to and including the RDS. That's inconsistent. If this were correct, my rate equation would have been rate is equal to K times conc of A times conc of B. But that's not what I observe in practice, so this mechanism is wrong. Well, this one is also wrong, because this says that 1B is involved up to and including the RDS. My rate equation should have been rate is equal to K times conc of B. That's not what I observe in practice. I observe rate is equal to K times A squared times B. So I can say all three of these mechanisms is inconsistent with the kinetic data, and therefore they're wrong. Well, let me propose a mechanism then that's consistent. So I can say perhaps maybe 2 A's plus B in one step might give C plus D. Maybe that's the mechanism. Or maybe, let's call this 1, or maybe 2 A's react to give Q. Q reacts with B in the rate determining step to give rise to maybe C and D. What do we call now? Yeah, C plus D. To give C plus D. Right? Maybe that's the mechanism. Whoa, that's exciting. Hey, stop that. Oh, come on. Or maybe there's a third option, which is, let's say that maybe 2A, let's say maybe B, oh crikey, may well be that, no, that's wrong, I didn't add these together, the Q's will go out. So that's 2A plus B gives C plus D. Or maybe I can say that A plus B gives W, W plus A in the, well, this W plus A gives Y, and then Y gives, let's say, Y plus C, then Y reacts with, Y breaks down to give D, let's say. When I sum those steps together, cranky. The W's would go out, the Y's would go out, and I'm going to make this step my RDS. So I end up with 2A's plus B gives C plus D. Now, 2A plus B gives C plus D. Now, since there's only one step, this will be the RDS. All of these mechanisms are consistent with what I have, which are the stoichiometry: 2A plus B gives C plus D, 2A plus B gives C plus D, 2A plus B gives C plus D. They are also consistent with my kinetics, because this says that 2A plus 1B, because my kinetics are rate is equal to K conc of A squared times conc of B. Right? So it says that 2A's and 1B are involved in the reaction up to and including the RDS. 2A's and 1B are involved in the reaction up to and including the RDS. 2A's and 1B are involved in the reaction up to and including the RDS. Now understand, here a Q is involved up to and including the RDS. Here a W and a Y are involved up to and including the RDS. But my rate equation can only feature the things I put in, my reagents, right? Because when I mix my reagents at the beginning, I can only mix the things that I have. If intermediates are generated, I can't put them in the system, right? I can't buy the intermediate. So what I buy are A and B, and I make C and D as my product. If the intermediates in the reaction are X and W and Y and whatever it is, I can't put those in. Those are generated in situ. So my rate equation only reflects the things I can manipulate, which are the reagents. So I don't care if there are many other things that are involved in the reaction. The point is, the reagent species involved are 2A's and 1B. Now I could ask you, draw the reaction profile diagrams for these reactions. And you will say, well, look, I know this reaction was an exotherm. Right? This was an exotherm. So I'm going to have enthalpy, reaction coordinate. Right? It was an exotherm, and in it I had 2A plus a B and made C plus D. There was no intermediate, so I went up the hill and I went down. And that plot is consistent with my observation. Single step, no intermediates. Well, what about this one? Well, this is a two-step reaction. Okay, it's still an exotherm, so 2A, and I'm going to end up with C plus D. And I'm going to have 2A plus B. Well, there's an easy step that gives rise to Q. It's a difficult step. Oh, good grief. I don't have enough room here. It's exothermic. So it's an easy step, and then it's a difficult step. So here I have 2A plus B. In the first step, both of the A's have succumbed. They generated in their stead Q. B was unaffected. So B is still present here. In the second step, Q and B react in a difficult step to make C and D. And the reaction is an exotherm. Let's look at the third one. I'm going to have to peek here because I don't quite. Yeah. In the third mechanism, right, it's still an exotherm. So I'm going to have H and reaction coordinate. still exothermic, right? I'm going to give myself some more room since I know there's 3 humps. In the first one, I have A plus B into something and something else. And it turns out the third step is the difficult step, right, to give rise to product. So I have 2A plus B, and then I have C plus D. So I'm going to populate the minima now. Well, I had 2 A's and 1 B at the beginning. In step 1, one of the A's and the lone B reacted. They made W. Well, that means then that one of the A's was left behind. The W and the A reacted to give Y and C. The Y reacted in a difficult step to give rise to D. The C, which had already formed, simply persists. So this would be a reaction profile diagram that's consistent with those data. Okay? Alright, I think that's a long enough lecture, and we'll stop there and we'll pick up from here on Monday. You guys have a good weekend. Bye-bye.